All right, let's finish off this example. So we knew that our fan was rotating at 188.5 radians per second. We figured that out before based on 1800 rotations per minute. The natural frequency of our support here was 192.56 radians per second. So we saw that they were pretty close, and we expected that we might get some sort of resonance going on. We measured the damping ratio experimentally, and we want to know a few things. We want to know a little bit more about this fan and what it's going to do, whether it's going to oscillate too much, if it's going to vibrate too much because it's near resonance. So suppose the fan has a rotating mass of 50 pounds, and we're just making an assumption here about how much of this mass is rotating and how much we expect that the manufacturing tolerances could be off by. And we're going to estimate that the center of mass could be located 0.04 inches from the axis of rotation, right? Doesn't sound like too much. And so the first question is, how much force, F naught, does this mass produce on the shaft, right? How much does the shaft have to react? And consequently, we're going to see that force here. That's going to be applied. It's going to be transmitted through the shaft to the body of the fan, and the fan needs to be supported by our structural section here. So we're going to have to react that force. So how much force are we going to see? So we've got a mass that is rotating at a distance r, and the force is mr omega squared. You've probably learned this in physics before, so we're not going to derive that this time. Right, we've got the centripetal acceleration, you might remember, is r omega squared. Maybe you've seen it written as v squared over r. Well, v is equal to omega r. So if you plug that in, we've got omega squared and r squared on top divided by r. You end up with an r times omega squared, right? And so that acceleration times that mass is equal to F naught. Let's figure out what that is. This mass was 50 pounds times 0.04 inches times our omega, not omega n, omega 188.5 radians per second. And that gets squared. That's going to give us 71064.5 in units of pound mass inches per second squared. But if we take that and we divide that by gravity, we can get it in units of pounds force. So we divide that by 386 inches per second squared. We know that because 1 pound mass is equal to 1 pound force divided by 386 inches per second squared. So we can take this pound mass, substitute it in there. That gives us dividing by 386 inches per second squared. And this is going to turn into pounds force when we do that. It's going to cancel out these units. So we're just left with pounds force. And we get 184.1 pounds force. So that's a lot of force, right? This thing swinging around that fast, it doesn't take a very much offset to get a pretty large force. So keep that in mind when you're designing rotating machinery. You have to have that center of mass really well tuned. And so sometimes what's done is after the fact, when you're creating rotating equipment, you'll add mass here and there or remove mass here and there to make sure it is very well aligned with the axis of rotation. Otherwise, you can get some very large forces. And those forces get amplified. We're going to see that in just a second. What is the amplitude ratio? There's a formula for this amplitude ratio. First of all, let's say that this force were just applied to the end of the steel beam, right? We know what the stiffness was. We determined the stiffness earlier. We said that K was equal to 11,528 pounds force per inch. 11,528. So if this force were just static, then we would expect that the force, F naught, divided by the stiffness, that would give us a deflection, right? F naught over K, and it would only deflect 0.016 inches. And we think, oh, well, that's not too much. But what about when it's dynamic? Well, then you need to multiply by this amplitude ratio. The amplitude ratio is, sometimes I call it alpha, 1 divided by the square root of 1 minus r squared. We're going to figure out what r is in just a second. That gets squared plus 2 zeta r squared. R is the frequency that you're actually rotating at divided by the natural frequency. So our R is very close to 1. We have 188.5 divided by our natural frequency, 192.56. So our R was around 0.979. When it's close to 1, what happens when this is 1? We saw in the preparation that when R is equal to 1, then 1 minus r squared is 1 minus 1. That becomes 0 over 2 zeta r, so that's also a 1, 2 zeta squared. And it's the square root of 2 zeta squared, so it's just like 1 over 2 zeta. So let's go ahead and use that approximation. 1 over 2 times 0.0458. Got an amplitude ratio of 10.917. That's quite a bit. So whatever this number is, our actual deflection that we see, the amplitude in steady state after a long time, you're going to have some, when you first start up the fan, you're going to have some transient behavior that dies down over time. It doesn't matter what the initial conditions were. Eventually, it's going to start vibrating at the same frequency as the fan is spinning at, omega, and with an amplitude of our f naught over k times the amplitude ratio. And so f naught over k was 0.016. All right, so it's now going to be oscillating at 0.175 inches. That's quite a bit. Like, what static force would it take in order to make it do that, to deflect by that much? Well, it's just 10.917 times that amount of force that we actually had. It would typically take 10.917 multiplied by the 184.1 pound force. It would take 2,000 pounds in order to make it deflect by that much statically. Right? So the effective force, I'll say EFF for the effective force that would be the same equivalent static load, is that amplitude ratio times F naught, 2,000 pounds. So it's much more. So what is the maximum stress in this beam? And it was 18 inches long. So the moment, the bending moment is going to, maximum way back here. We've got something like this effective force being applied at the end. The bending moment would be the length 18 inches times 2,009 pounds. That is 36,176.75 pounds force inches. And the stress is my over I, or mc over I. C in this case is just an inch. And I was 0.747 from the steel manual. So we just need to divide by 0.747. We get a stress of 48.43 KSI. That's quite a bit for most materials, right? If we were using some sort of mild steel, this is going to be too much for it. And so then you ask, well, how do you remedy the problem? That's a good design question. So let's see. Oh, one more thing. That's the maximum stress. What's the reaction force at the wall? It's actually not this effective force. It's even more than that. And the reasons, if you do the math, it makes sense. We're used to statics, right? We're used to whatever force we apply out here to be the force that we see here. But when we've got accelerations involved, that all bets are off as far as that goes, right? The statics only works when there's no accelerations. But we've got accelerations. So it turns out that the force at the wall is different. The reaction force is this force transmission ratio. The force transmission ratio times F naught. So the reaction force at the wall is F naught multiplied by this square root of 1 plus 2 zeta r squared, and that is over the square root of 1 minus r squared, same thing we had before, plus 2 zeta r, and that is squared. So I think that what I'm going to do is say that r is 1 again. And I'm going to say square root of 1 plus 2 zeta. So it's 4 zeta squared. But actually zeta is really small. It's not going to be too different. Remember that zeta is 0.0454, I think. 458. Yeah, I get very close. It's 10.96. So theoretically, times F naught. So it's very close to the, what do we have before, 10.917. So we're applying almost 2,000 pounds, or a little bit more than 2,009 pounds back to the wall. So got to check those welds, see if those are going to be able to handle it too, I suppose. Or if you had bolts, that's the sort of loads that you would see back there. Now, how do you fix this, right? The obvious thing is, well, we need a bigger, the stress is too high, so maybe we need something with a larger moment of inertia. That might be a way to fix it, but actually, right, a lot of our stress is coming from the fact that we had this big amplitude ratio. This alpha was big, and that came from the fact that our R, our omega over omega n, was very close to 1. What if our natural frequency were to change? If our natural frequency were to change, then we can bring this R far away from 1, and maybe we can get, by changing this omega n, we can reduce the amplitude ratio. And one way to change omega n is to make it bigger, and we think, oh, that's going to reduce the stresses. That's true, but hey, what if we make it lighter? What if we made a lighter section? If you use a 2 by 2 by 1/8? Let's try that. Instead of the 2 by 2 by 1/4, we use 2 by 2 by 1/8. So if you look that up in the steel manual, then I is 0.486 inches to the fourth. If you go through the same sort of calculation that we did before, omega n would turn out to be around 150, and I'm rounding quite a bit here, radians per second. That's very different than what we had before. We had 188.5 192.56 radians per second before. So let's see what that does to our amplitude ratio and all that. Okay, so now R is going to be 188.5 divided by 150. It's around 1.25. If we plug that in, let's figure out what our amplitude ratio, alpha, is. I would say that R is not close enough to 1 to use that approximation anymore, right? So it's 1 minus R squared, 1 minus 1.25 squared, that gets squared, plus 2 zeta, zeta is 0.054, right? 0.0458, excuse me, times R, times 1.25. That gets squared as well, and we get the square root of all that. I'm getting something like 1.742. So all we had to do was change the natural frequency a little bit. So that's going to reduce our forces quite a bit. We're going to have, instead of an amplitude ratio of 11 or so, or 10 or something like that, it's only 2. So let's figure out what the stress actually is, right? Because our I has changed as well. So let's calculate the new stresses. We're going to need to know what the force is. The force effective is equal to F naught times the alpha, where F naught was 184.1 pounds. And then we're going to multiply by the 1.742. So that's like there's 320 pounds of static force on our beam. Let's figure out the stress from that. The sigma is equal to mc over I, but c is just 1 inch. The m is 320.7 times 18 inches divided by 0.486, and we get 11.878 KSI. So we brought our stresses down by a factor of, about 4 relative to what we had before by counterintuitively reducing the thickness of our section.